Okay, so I hope you had a good time with the holiday. Now it's time, we are rested. Now it's time to get started. Now, as some of you might be aware, there has been an update to the notes which we were looking at last week. So the notes have been updated a bit to include certain things which eventually, as I was trying to teach, I felt from last week that those things need to be added. And I'm going to highlight those updates so that you can see and also can make reference. So if there is something which was not very clear last time, you probably this time around is going to be a bit clear. The first updates I want to highlight is on the example number 1. We worked out how many radians the pendulum was working to be 0.17 radians, and this is how you change your radians into degrees. So you have your radians here, which is the angular displacement, 0.17 radians, then you multiply by 360 degrees, then you divide by 2 pi radians here, and when you do that, so this rad, the rad which you have here, and this rad which you have here, they'll cancel out. Then 0.75, 0.117 and 2 pi you divide, then you multiply by 360, so you should have approximately 9.74 degrees. So that's the first update which was added to the notes. Next update to the notes was the relationship between the velocity v, or the tangential velocity, and the angular velocity omega. So in this case, from this relationship, we defined angular velocity omega to be the total angular displacement divided by the time it takes to make that particular angular displacement. Now, from this relationship, which we have here, equation number 5, we know that the angular displacement omega, the angular displacement is equals to this. Equation number 3. Sorry, theta, the angular displacement theta is equals to S divided by R, which is the linear displacement divided by the radius of the circular path. So if we do that here, we substitute for this. For theta, we substitute S over R. This is what you have here. That's what you've done. S divided by R, substitute for theta. Then when you write this, you end up writing this as S divided by R, which is the radius, and the T, which is the time. Then you can write this expression in factored form. You can write it as omega is equals to S divided by T 1 over R. Now this S divided by T is just the velocity V here. V, or your average velocity, is equals to the displacement divided by the time. So this bit here, this part here gives you V. Then you multiply your V multiplied by 1 times R, 1 over R there. So you end up having omega is equals to V multiplied by 1 over R, which gives you omega is equals to V divided by R. If you multiply both sides by R, you end up with V is equals to the radius multiplied by the angular velocity. So this is the relationship we used in one of our examples last week. I felt that it's important that you see where this relationship comes from, and I think this is a very simple way of showing how the velocity v is related to the angular velocity omega and r, which is the radius. So you have v is equals to the radius multiplied by omega with equation number 7. Is that clear to everyone? How v, the velocity in meters per second, is related to omega in radians per second?
Yes.
Okay. The other relationship which we used is one which relates the acceleration, our linear acceleration, to our angular acceleration. Okay. Before we go to that, this relationship was not properly written. There was a minus here, and there was here in place of the plus, there was a minus, and at the bottom here there was a t. So it wasn't properly written. So the average, it's still not properly written, basically, in my opinion. So there's still, yeah. So, yeah. Okay, we'll skip it. I'll make the change later. Then there was here, this other thing was the conversion from revolutions per minute. How do you convert revolutions per minute to radians per second? So basically what we showed, this I rewrote so that I think it's now clear exactly what it is I was trying to do. So here you've got 480 revolutions per minute. So you can write this as 408 revolutions divided by 1 minute. So this 480 revolutions divided by 1 minute, you have to change these into radians per second. So how do you do that? It's going to be 408 revolutions divided by 1 minute multiplied by 2 pi radians divided by 1 revolution. So this revolution here, this revolution will cancel out this revolution. Then you have 1 minute divided by 60 seconds. So this minute here, it's 1 minute here, will cancel out this 1 minute here. So in that case, when you do this, when you multiply like this, you get rid of the revolution with that. You also get rid of the minute with this. So the only units which are going to be left to be radians and seconds. So in that case, you're going to multiply your 480 multiplied by 2 pi radians, then divided by 60, then you end up with 50.3 radians per second. Is this clear? Is this conversion from revolutions per minute to radians per second clear now to everyone? What factors you multiply with for you to change?
It is, sir.
Okay.
Exactly.
All right. So that's the other thing I wanted to highlight. Same thing here also. Changing our 900 revolutions per minute into radians per second. So you have 900 revolutions there. You have got 1 minute here. So you write your 900 revolutions divided by 1 minute. So you multiply by 2 pi radians divided by 1 revolution. Then you also multiply by 1 minute divided by 60 seconds. So this 1 revolution here, this revolution, you cancel out this revolution. The minute up there will cancel out the minute at the bottom here. So you remain with only radians and seconds. So you end up having 900 multiplied by 2 pi divided by 60. You end up with 94.2 radians per second. So that's how you convert from revolutions per minute to radians per second. Of course, we have shown where this formula comes from. V is equals to radius multiplied by the angular velocity and how to use it. The other formula which we used but did not show how we get it is one which connects the linear velocity to the angular velocity. So of course, first you start from here. So this is how we defined our angular acceleration. Angular acceleration is equals to the final angular velocity minus the initial angular velocity divided by the time. Now we know from here, we know the relationship between our angular velocity and the linear velocity. Omega is equals to V divided by R. So this relationship is known. So we can write our final angular velocity and our initial angular velocity in terms of a final velocity and initial velocity as follows. Omega I is going to be equals to Vi divided by R. Then omega F is going to be equals to Vf divided by R. With these substitutions, we can substitute for these here. When we make those substitutions, we end up having alpha is equals to Vf divided by R minus Vi divided by R, divide the whole thing divided by T. Next, we can factor out the radius 1 over R. So we can factor out 1 over R like this. We end up in brackets here, you end up with Vf minus Vi, then the whole thing divided by T. So if that's a factored thing, we can bring it in front here. So we will remain with Vf minus Vi divided by T. So you end up with your final velocity minus initial velocity divided by time. But your final velocity minus initial velocity divided by time is just your acceleration a. So a is equals to vf minus vi divided by t, like that. So this whole thing in brackets, this whole thing we can replace with a. So we end up with alpha is equals to a divided by r. Then you multiply both sides by r. When you multiply both sides by r, we end up with a is equals to r alpha. So this is the other relationship which we used last week. So basically that's how you come up with those relationships. Is it clear? Is it clear to everyone now?
Yes, sir.
Okay. Is there any question? Okay, if there are no questions, again, these are just conversions I've rewritten like that.
Sir,
Yes.
I just wanted to ask, what are the SI units for angular displacement?
Radians.
Oh, thank you, sir.
Then for angular velocity, radians per second. Then for angular acceleration, radians per second squared.
I've understood, sir.
Oh, okay, fine. So these are the three relationships. From those three relationships, S is equals to R theta and V is equals to R omega. So this one, S is equals to R theta, V is equals to R omega, then A is equals to R alpha. These three equations, they give us a connection between the physical quantities we use to describe motion in a straight line with the physical quantities we use to describe motion in a circle. The S is the linear displacement, which is displacement in a straight line. The theta is the displacement, the angular displacement, which is displacement in a circle. The V is your speed or velocity in a straight line. Then your omega is how fast that particular object is rotating or is going around the circle. Then your A is your linear acceleration in a straight line, how fast the velocity is changing. Then your alpha here is how fast the speed of this particular object which is rotating or moving in a straight line circle is moving. So apart from these relationships, there are also other relationships which we can come up with. There are other relationships which can come up with. For example, we have the relationship for average velocity. We know that we can work out the average velocity. V is the velocity, then AV is the average. This is equals to half the final velocity plus the initial velocity. We can get our average velocity like this. Okay. Now, we are talking about velocity in a straight line here, and we want to find what formula does the same thing when you're moving in a circle. So we substitute for V. We know that V is equals to R omega. V is equals to R omega. So wherever there is V, we put R omega, and it carries the same subscript. So so in this case, your V average is going to be equals to R multiplied by omega average. That is equals to half. Then your final velocity VF, the VF is going to be equals to R omega F plus your initial velocity VI that's going to be R omega I. So with this, you can see that there is R on the left hand side, there is an R on the right hand side, which you can factor out of these parentheses. When we factor the R out of these parentheses and cancel out with this R, what we remain with is this one here. We remain with omega average. Omega average is equals to half omega I plus omega F. So this is how you get your average angular velocity. Average angular velocity is equals to half your initial angular velocity plus your final angular velocity. So you add the initial angular velocity plus the final angular velocity, then you divide them by 2, then you get your average angular velocity. As you can see, this equation number 25 is a carbon copy of this equation number 23. They are the same, except here where we have got average velocity, we have written angular velocity. Here where there is final velocity, final linear velocity, we have written final angular velocity. Here we have got initial linear velocity, we have written initial angular velocity. The half stays the same, so there is no change there. So basically you can see that this equation which you have here and this other equation which you have here, they are carbon copies of each other. Is that clear? Equation 23 and equation 25, they are carbon copies of each other. Is that clear?
Yes, sir.
Now, the realization that some equations are actually carbon copies of each other will save you a lot of time, and it will make you working out problems of motion, whether it's circular or linear motion, it will make it very fast, because you can work with whatever you're comfortable with. But sometimes it's also sometimes it's easier to work with circular, then you move to linear, or sometimes it's easier to work with linear motion, then you move to circular stuff. Okay. Another equation which we have come across is one which gives us the linear displacement. We know that the linear displacement S is equals to the average velocity multiplied by the time. So the displacement which is covered by an object is equals to what the average velocity is multiplied by the time. So in this case, we know how S is related to omega. We have this relationship. S is equals to r theta. We also have the relationship. We know how average velocity, AV, average velocity is related to omega. We have this relationship. AV is equals to r omega. So with these substitutions, we can make these substitutions and we see what we're going to have. So when we substitute for S here, in place of S, we write r theta. So we're going to end up having r theta equals to, then for this one here, the average velocity, remember velocity, V is equals to this. V is equals to r omega. So if it's average velocity, then at the end of the day, that side you're also going to have your average angular velocity. So you're going to end up with this bit here, r omega average multiplied by time. So that's what you're going to have. Then there's r on the left hand side, there's r on the right hand side. So you cancel them out. So you're going to remain with this. You're going to remain with theta is equals to average angular velocity multiplied by time. Again, if you look at this, S is equals to average velocity multiplied by time, equation number 26, and you look at this, the angular displacement is equals to average angular velocity multiplied by time. They're just the same thing. They're carbon copies of each other. Equation 26 and equation 28 are carbon copies of each other. How? This S is in a straight line, but when you're moving in a circle, S turns into theta. Then this V here, V is when you're moving in a straight line, but when you're moving in a circle, V turns into omega. Then of course the time remains unchanged. So far we have seen two equations which are carbon copies of each other. The good news is that going forward, you're going to see that there are actually more of your equations of motion. They turn out to be carbon copies of each other, and that should make life very easy. For example, you have got this equation, V with the final velocity is equals to the initial velocity plus the acceleration multiplied by time. This is one of the equations of motion. But what you're going to do here is we want to find a copy of this equation. This is an equation in a straight line, but you want to find a copy of this equation which applies when you are moving in a circle. So we know that our final velocity, we know that the velocity V is given by this. V is equals to r omega. Then we've got A here, which is acceleration in a straight line. The acceleration A is equals to r alpha. So we're going to substitute for V. For V, we're going to put r omega. Then for A, we're going to put r alpha. So for final velocity, Vf, we're going to end up with r multiplied by omega f equals to r, this Vi here. So Vi is the initial velocity, so that's going to be r, then omega I plus this A is a linear acceleration A, and we know that A is equal to r alpha, so that's going to be r alpha t. Then there is, of course, there's an r this side, there's an r there, you can factor out the r, then there's an r this side. If you factor out the r, then you cancel them, then when you do that, you're going to end up with omega f is equals to omega I plus alpha t. Your final angular velocity is equal to the initial angular velocity plus the angular acceleration multiplied by t. This equation, which is equation number 31, is a carbon copy of equation number 29. Vf is equal to Vi plus alpha t. This is the third equation, which is a copy of an equation we know. So the good news is this thing repeats itself. Whichever equation you have, as we are going to show, there is a copy of that equation in circular motion. So you just need to know what to replace. You replace s with theta, you replace v with omega, you replace acceleration A with alpha. Are we clear?
Yes, sir.
Yes, sir. Thank you.
Okay. Next, there's this other equation. S is equals to initial velocity multiplied by time plus half at. So in this case, we know S, which is a displacement, linear displacement. S is given by this. The S is equals to r theta. Then our V is equals to r omega. Then our Vi is equals to r omega I. Then our acceleration A is equals to r alpha. So in this case, when we substitute for S, we put r theta. Then for Vi, we put r omega I t plus half r alpha t squared. So in this case, again, there's an r this side, there's an r here, there's an r there. We can factor out the r's and cancel them. When you do that, we end up with theta is equals to omega I t plus half alpha t squared. Again, you see that this equation, equation number 34, is an exact carbon copy of equation number 32, where there is S here, we have replaced it with theta. Where there is initial velocity, we have replaced it with the initial angular velocity. Then where there is the linear acceleration of A here, we have replaced that with alpha. Again, another equation which is exactly a copy of the other one. Next, there is last but not the least, there is this equation. The final velocity squared is equal to the initial velocity squared plus 2as. Okay, so in this case, well, we know the velocity v is this r omega. Then there is acceleration A is r alpha. Then there is s is r theta. So when you substitute there, you're going to have r omega f squared equals to here Vi r omega I squared plus 2. Then in place of A, we put r alpha. Then in place of S, we put r theta. Then we multiply. Expanding and simplifying, we end up with r squared omega f squared equals to r squared omega I squared plus this r and this r, they multiply, you end up with r squared. Then there is an alpha and then theta, they end up with alpha theta at the end. So there is an r squared here, there is r squared there, there is r squared here. So this one and this one you can factor out, then cancel, you end up with cancelling that r squared and that r squared. When you cancel that, you end up with omega f squared is equal to omega I squared plus 2 alpha theta. this. Equation 38 is a carbon copy of equation 35. Is that clear?
Yes, sir.
So what you notice is, apart from those three relations, S is equal to R theta, V is equal to R omega, and A is equal to R alpha, the other 5 equations of motions, they're just carbon copies of each other. And I think we have a table showing the same here. So this table shows what we have done so far. So this equation, its angular counterpart is this one. For this equation, the angular counterpart is this one. For this equation, the angular counterpart is this one. For this equation, the angular counterpart is this one. For this equation, the angular counterpart is this one. It's enough to not only know the ones in a straight line, these ones, but if you're going to, what is the circular equivalent of this equation, you have to replace S with theta, you have to replace V with omega, you have to replace A with alpha, so that you can get these other equations this side. Are we clear? Any questions so far on what we have done?
No, I'm clear, sir.
Okay, so let's look at some examples and see how we use this information which I've come up with. Okay, so here, example number 5, a belt passes over a wheel of radius 25 centimeters as shown in figure 2. If a point on the belt has a speed of 5 meters per second, how fast is the wheel turning? Of course, so what we have is a wheel like this. This is a wheel which you have, and of course the belt is going around like that. So if a point on this belt is moving with a speed of 5 meters per second and the radius of the wheel is 25 centimeters, then how fast is the wheel rotating? So if you know the speed with which any point passes on this particular wheel, which is 5 meters per second, then you can find out how something is turning, how fast the wheel is turning, by using this relationship which we have here. V is equals to R, which is the radius of the wheel, multiplied by omega, which is how fast the wheel is turning. The V here is the velocity of the point. So since we're looking for how fast the wheel is turning, we make omega the subject of the formula. Omega measures how fast something is turning, or how fast something is spinning. Okay, so we end up having omega is equals to V divided by R. So when something is turning or spinning, how fast is it turning or spinning? That is what omega is. Are we clear? Omega, the angular velocity, is
Yes, sir.
the angular velocity is a measure of how fast an object is turning, for example, a wheel, or how fast something is going around in a circle. Okay, so in that case, we're going to have a velocity of the point. V is equals to 5 meters per second divided by the radius. Now this radius has to be in meters. So we've been given a radius in 25 in centimeters, 25 centimeters. So you need to change this 25 centimeters into meters, and you're going to end up with 0.25 meters. So 0.25 meters. So 5 meters divided by 0.25 meters, you're going to end up with this. You're going to end up with 20 radians per second. Again, this meter and this meter are going to cancel out. So if the meter, which is a unit for distance, cancels out, then what's going to remain is a radian. A radian also measures distance, but it measures distance in an angular way. Okay, so you end up having your angular velocity as 20 radians per second. This is how fast it's turning. So every second it covers 20 radians. Is that clear?
Yes, sir.
Okay. Example number 6. A pulley of 5 centimeter radius on a motor is turning at 30 revolutions per second and slows down uniformly to 20 revolutions per second in 2 seconds. Calculate A, the angular acceleration of the motor. how fast the pulley slows down. And for us to do this, we have got this 30 revolutions per second. 30 revolutions per second is how fast something is turning before we start measuring the time. So this is the initial angular velocity. Then the 20 revolutions per second is our final angular velocity. And how much time does it take to slow down? 2 seconds. So what we have here is angular velocity in revolutions per second. However, you are not supposed to do your calculations in the revolutions per second. If you want to do your calculations, you need to turn these revolutions per second into radians per second. So in this case, this 30 revolutions per second is our initial angular velocity. Omega I is 30 revolutions per second, but we need to turn 30 revolutions per second into radians per second. So how do we do that? We write omega I is 30 revolutions per second. That's going to be 30 revolutions divided by 1 second. So this is going to be 30 revolutions divided by 1 second multiplied by 2 pi radians divided by 1 revolution. So why are we doing this? This revolution and that revolution will cancel out. We will remain with a radian and will remain with a second. So it's going to be 30 multiplied by 2 pi divided by 1 second. So you end up with 188.5 radians per second. So this is how you change your revolutions per second into radians per second. Is it clear on how we do the conversion from revolutions per second into radians per second?
Yes, sir.
Next, it slows down to 20 revolutions per second. So again, we need to change this final angular velocity, the omega f of 20 revolutions per second into radians per second. So that's going to be omega f is going to be 20 revolutions per second equals to 20 revolutions divided by 1 second. This is going to be 20 revolutions divided by 1 second multiplied by 2 pi radians divided by 1 revolution. This revolution and this revolution down here will cancel out, so you end up having 20 multiplied by 2 pi radians divided by 1 second, and you're going to get 125.7 radians per second. So this is how the conversion is done. So it's very important that everything, all calculations have to be done using SI units. The SI units for angular velocity are radians per second. If you do your calculation in units which are not SI units, then you're going to get your answer wrong. So in this case, we can now, since we now know what our initial angular velocity is, 188.5 radians per second, and we know our final angular velocity, which is 125.75 radians per second, we can work out the angular acceleration since we know how much time it takes. The time it takes is 2 seconds. So in this case, we have alpha, which is the angular acceleration. The angular acceleration measures how fast this particular pulley is going to slow down. So in this case, alpha is going to be equals to omega f minus omega I divided by t. So omega f is 125.7 radians per second minus 188.5 radians per second divided by 2 seconds. So this on top here, when you work out the calculation, you're going to have alpha equals to minus 62.8 radians per second. Then at the bottom here, 2 seconds. If you then you work out this thing, you're going to have alpha equals to minus 31.4 radians per second squared. This and that. So you end up having a second squared there. So that is your angular acceleration. Your angular acceleration has got units of radians per second squared. Next, as it is slowing down, as the pulley slows down from 30 revolutions per second to 20 revolutions per second, it's a pulley, so it has to turn. So the question is, how many times does it turn? How many revolutions? Here. Now, for us to find the number of revolutions, we first need to find the angular displacement in radians. If you want to find the number of revolutions, we first need to find the angular displacement in radians. And we have got one of the formulas to do that. Theta is equals to omega I multiplied by t plus half alpha t squared. This is one of the formulas we came up with, so we can use this since we are looking for the number of revolutions, which is a measure of angular displacement. You can measure your angular displacement using radians. You can measure your angular displacement using revolutions. You can measure your angular displacement using degrees. When you're doing your calculation, you have to do everything in radians. So first we need to find what is the angular displacement in radians. Then after we do that, then we can change the radians into revolutions. So in that case, so when you do this, our initial angular velocity is what we have here, 188.5 radians per second, multiplied by the time, which is 2 seconds, plus half. Then the angular acceleration we've just found here is minus 31.4 radians per second squared, multiplied by the time squared, which is 2 seconds squared. That when you work out this whole calculation, you punch all these things, all these numbers in your calculator, you end up with theta is equals to 314.2 radians. So this is your angular displacement, but your angular displacement is in radians. The question is looking for the number of revolutions. That's what the question is looking for. How many revolutions? What we have is the displacement in radians. Now we know something about revolutions and radians. We know that 1 revolution is equals to 2 pi radians. So if you want to find the number of revolutions, we need to multiply our angular displacement, whatever our angular displacement is, we multiply it by 1 revolution divided by 2 pi radians. So we multiply it by this factor. So in this case, our angular displacement is 314.2 radians times 1 revolution divided by 2 pi radians. Why are we doing this? We are multiplying with this factor so that we end up with revolutions and we cancel out the radians. This radian at the bottom, this radian here, and this radian here will cancel out. So what we end up having here is, when they cancel out, we'll end up having 314.2 divided by 2 pi multiplied by revolutions. So we end up with approximately 50 revolutions. So the pulley, which is whatever it is, 5 centimeters radius, will have to turn 50 times during this 2 seconds. Is that clear?
Yes, sir.
Okay. Next.
Sir, I've got a question.
Yes.
So, can you also find the angular displacement when you use that other formula?
Yes. This is just one way of finding the angular displacement. This is not the only way of finding it. Remember, we know this. We know omega f. We also know omega I, and we also know the time, right? So there is this other formula here. Where is that? This. You can also use this. Theta is equals to average angular velocity multiplied by the time. But how do you get the average? Average angular velocity is equals to half, then omega I plus omega f. So if you get your omega I, which is a 125.7 or something, or 5 plus 188.7, then you divide by half, it's going to give you this. Then this, you put it here, then you multiply it by 2 seconds, then you get this. So there's more than one way of finding your angular displacement. You get the same answer, I'm sure. Any other question? This seemed to be, that one I was showing up there is a 2-step process for you to get the angular displacement. But this one is just a 1-step process where you just substitute your things, then you work out the calculation, then it comes out like this. So you get your angular displacement in radians, but the question is asking us to find the angular displacement in the revolutions. So you need to change those radians into revolutions. Are we clear? Okay.
Yes, sir.
The length of belt, it winds in this time. So we know length is displacement. Okay, length is displacement. So length in this case is given by the s. The length is given by the s, but what we have is this. Theta is equals to, the angular displacement theta is equal to 314.2 radians per second. Radians. So we know we're looking for length s. So s is going to be, the length s is going to be equals to the radius of the pulley multiplied by the angular displacement. So we just multiply the r times theta. So in this case, s is going to be equals to, we know the radius is 5 centimeters, so that's going to be 0.05 meters multiplied by the angular displacement, which is this. So in this case, yeah, there is a second here which is not supposed to be here. So the second is not supposed to be there. It's just supposed to be radians. So you multiply 0.05 meters multiplied by the radians. So you're just supposed to end up with 15.7 meters. So approximately 15.7 meters. That's how much belt is going, the pulley is going to go, which is going to unwind through the pulley in this particular amount of time, in 2 seconds. So this second is not supposed to be there. Is there any other question? Any question?
No questions, sir.
Yeah. So you notice one thing here. The first part of the question here, it's talking about angular motion. Even the second part is talking about angular motion. But from this angular motion, we have been able to jump to find how much distance is covered by the belt in this particular time. So you can move between, it depends on what's more convenient. You can do your calculation in angular, using angular formulas. Then at some point you can change to what's easier to, if you're asked to find something in linear, you can change. You can use whatever, one of those simple equations, then you change. Okay. This other equation, this other example has got something.
Sir, I have a question.
Yes.
So in other words, the equations can be used interchangeably?
Exactly. That's what I've been trying to say. You can use these equations interchangeably,
Okay,
depending on what's convenient. Also, the question itself will tell you whether to start with circular equations, then later on move to linear equations, or you start with linear equations. It's easier to start with linear equations than move to circular equations, as you can see from the next example. Example number 7. A car has wheels of radius 30 centimeters. It starts from rest and accelerates uniformly to a speed of 15 meters per second in a time of 8 seconds. Find the angular acceleration of its wheels and the number of rotations one wheel makes in this time. So of course, we have been given the radius of the wheel, which is 30 centimeters, but most of the information you have been given, apart from the radius of the wheel being 30 centimeters, most of the information you have been given concerns a car which is moving in a straight line. We are told it starts from rest. So if a car starts from rest, its velocity is 0 meters per second. Then it accelerates to a speed of 15 meters per second. That's its final velocity. And the time in which it does all this is 8 seconds. So most of the information you have been given here is information which has to do with this vehicle moving in a straight line. So you can use your straight line formulas. Okay, for example, we are asked to find the angular acceleration. But it's possible for you to find the angular acceleration from linear acceleration. If you can find the linear acceleration, after you find the linear acceleration, because you know what the radius of the wheel is, then you can find the angular acceleration, and that's exactly what I'm going to show. So here we are going to go the straight line way, then later on, at the end, then you're going to switch into angular. So here, the linear acceleration A is equal to the final velocity minus the initial velocity divided by the time. Our final velocity is 15 meters per second. Our initial velocity is 0 meters per second, and the amount of time it takes our car to move from 0 to 15 is 8 seconds. So in that case, you substitute, you end up having 15 meters per second minus 0 meters per second is equals to 8 seconds. And that's going to be A equals to 15 meters per second divided by 0.8 seconds. You end up having A is equals to 1.9 meters per second. This is naturally what you do. But the question is not asking you for your linear acceleration. It's asking you for your angular acceleration. So from your linear acceleration, you know that your linear acceleration is 1.9 meters per second squared, but you know that linear acceleration A is related to angular acceleration like this. A is equals to r alpha. So you can find your alpha. Alpha is equals to A divided by r. So in this case, if you're looking for alpha, which is the angular acceleration, which is what we have been told to find, that's just going to be equals to 1.9 meters per second squared divided by 0.3, and that's going to give us an alpha, which is approximately equals to 6.3 radians per second. This is an easier and faster way of doing things than if you had decided to start changing everything. You change this 15 meters per second into, you can change it also. You can change it in, it's up to you whether you do it like this or you change your 15 meters per second into final angular velocity. That's also up to you. You can do all sorts of things you want because you know what the radius is. So whether you want to change everything into secular or you want to start with linear then move to secular, it's really up to you what you want to do. Choose a method which is easier for you. Are we clear? This is not the only way to solve this problem. But I've chosen this to show that you can start with a quantity like acceleration, which is a straight line unit involved in straight line motion. Then you change this acceleration into angular using this expression, which is an expression which we know. A is equal to r alpha. Then you do that, then you get your angular acceleration in radians per second squared. Are we clear?
Yes, sir, but I have another question.
Yes.
I have noticed that you're using the approximate sign when writing the final answer. Is it always like that? Is it wrong if you put the equal sign?
Usually, because I don't think it's, I think I kind of rounded off something. But you can put an equal sign. I don't think we care very much, since most of the physics which we do is just approximating something, whatever you're trying to estimate.
All right.
Yeah. Next, we know the initial velocity is this much, 0 meters per second. The final velocity is 15 meters per second. We know the time is 8 meters per second. We want to find the number of rotations or the number of revolutions which the wheel makes in this time. Again, you could do that using a secular method, but I have chosen to use this since I know what u and v are and time, so I can work out s. So s is equal to half u plus v multiplied by t. So the u is 0 meters per second, the v is 15 meters per second multiplied by the time, which is 8 seconds. So in this case, it gives me a linear displacement which is equals to 60 meters. So basically, during this particular time, this car covers a distance of 60 meters. But that's not what I've been asked to find. What I have been asked to find is the number of rotations the car is going to make during this time. So in that case, since I know that the car covers a distance of 60 meters and I know that the radius of the wheel is 30 centimeters, so 30 centimeters in 2 meters is going to give me 0.3 meters. So I can use this information, I can use the 60 meters and the radius information to find out what is the angular displacement which the wheel covered in this amount of time. So theta is going to be s over r, so that's going to be theta is equal to 60 meters divided by 0.3 meters, and that's going to give me theta equals to 200 radians. So this is the angular displacement, 200 radians. How did I get the 200 radians? I got the 200 radians from s, which is 60 meters. I divide it by the radius, and that's what I get. So with the 200 radians, now I can change these 200 radians into revolutions. And how do I do that? Number of revolutions is equal to theta multiplied by 1 revolution divided by 2 pi radians. So here, I've got 200 radians times 1 revolution divided by 2 pi radians. So this rad and that rad will cancel out. So I'll end up with 200 divided by 2 pi multiplied by that revolution. So I'll end up with 31.8 revolutions exactly, and 31.8 revolutions is just approximately 32 revolutions. We have come to the end. Are we clear on how we interchangeably yes?
Sir, for the question.
Yes.
Yeah. Is it advisable always to include the units in each and every step when you're solving a question?
How are you going to know? No, not you have to know that if you are working out S has got units of meters. If you already know that S has got units of meters, then you can skip units in these calculations. But if you're not sure what kind of units S has, I would advise you to include the units, because what some students do is they sometimes you give this theta, you give it units of meters. It means that you don't understand what it is you're doing. You give theta units of meters, you end up giving S units of degrees. So in order for you to avoid such mistakes, because such mistakes when you're writing a test and you're writing an exam, you make a mistake but you're not aware that you're making a mistake. Are you clear? Because what you think you're doing the right things, but because you're not using any units, there's nothing to guide you as you're doing this gymnastics of doing back summers from meters to radians, coming this like that. As you're doing these things, you have got you're not okay. Here I know it's radians because I've cancelled the meters and meters. I've cancelled them. That's how I know that it's going to be radians. If you cancel out the meters, what you remain with are radians. Are we clear?
Yes, sir. Yes, sir.
Yeah. So I would advise you to put the units there so that you can see, you're sure about the units of the final answer. If you already know what the units of the final answer are, fine. I don't have a problem with that. The only thing is, when I mark your script or someone marks your stuff, it's only your script speaking for you. So we will not be able to say, okay, so where did you go wrong and stuff like that. That will not be able to happen. Any other question? Okay, so if there are no other questions, we have come to the end. So we'll meet tomorrow. Last week we couldn't meet because last week suddenly became a holiday. So that's why we couldn't meet. So we'll catch up. Tomorrow we'll continue looking at what's called centripetal acceleration and centripetal force. Okay. Now, we'll discuss what centripetal is tomorrow. Unless there are any questions, we end here. We have come to the end of our class. So I'll see you tomorrow. The video is being recorded, so the recording is going to be uploaded to YouTube within the hour. Maybe those other people, they can check by 20 hours. There should be a recording on YouTube. Okay, so we have come to the end. See you tomorrow if there are no further questions.